Okay, I was saying that what if our numerator and denominator be some crazy polynomials which factoring be not easy, like the numerator and the denominator of this fraction. Here in the numerator, the last term is minus 27, and it is not x to the 27, it is minus 80x minus 27. Okay, now how would you factor the polynomials in order to simplify the fraction? The best way is using the rational root theorem. If you're not familiar with it, please check out the videos how to factor the crazy polynomials in the factoring polynomials playlist. Okay, according to the theorem, we should substitute the divisors of the constants into x to see which ones make them vanish. So we should begin by substituting plus and minus 1, then plus and minus 3, then plus and minus 9, and finally plus and minus 27 to see which ones make them equal to 0, and 27 is the number which make the both equal to 0. I know that I made the polynomials. Okay, but how about this? Here the constant terms do not have a huge number of divisors because their divisors are just plus and minus 1 and plus and minus 2. But none of them makes the polynomials vanish. So rational root theorem doesn't work here. So the best way to simplify a fraction like this is calculating the greatest common factor or divisor of its numerator and denominator, and then dividing them by the greatest common factor or divisor. But how could we calculate their greatest common factor? One way would be by division. This way, according to the remainder theorem, for two polynomials f and g, f of x equals to g of x times q of x plus r of x, in which q of x is the quotient and r of x is the remainder, which degree is smaller than g of x. Now, showing the greatest common factor of f and g as c of x makes f of x equal to c of x times another polynomial like f1 of x, let's call it as f1 of x, and the g of x as c of x times another polynomial, let's call it as g1 of x. Now, subtracting c of x times g1 of x times q of x from the both sides of this makes it equal to this. Okay, and now on the left, the both terms got c of x, so we could factor the left side as this. Now let's show this one, which itself is a polynomial, as a of x. So R of x would be equal to C of x times A of x, which means that C of x is also a factor of R of x. So that means that R of x got the greatest common factor of f and g. Then to calculate the greatest common factor of f and g, you could calculate the greatest common factor of f and r or g and r. And since the degree of g is smaller than the degree of f, so it's better to calculate the greatest common, and it's easier to calculate the greatest common factor of g and r instead of g and f. And finally, you may be asking that, okay, C of x is a factor of R of x also, but how do we know that it is the greatest common factor of R and G, for instance? And it's not just any common factor. To answer that, suppose R and G got some extra common factor, which F doesn't have. Now, in the relation of the remainder theorem, on the right side, the terms on the right side should have the extra common factor. So we could factor the right side as the extra common factor times another polynomial. And that means that f of x equals to the extra common factor times the other polynomial, which means that f of x also got the common factor. So the assumption that R and G got some extra common factor which F doesn't is wrong. So that means that C of x is the greatest common factor of R of x and G of x, or R of x and F of x, also F of x and G of x. To make it more clear, I give you some examples in the next videos. Okay, thank you.